What do you think? That's a good question. 20 and 100 में तो बहुत फर्क हो जाता है. It is graded out of 20. So the marks that have been given are been very liberal. The reason for the liberal marking is in spite of my disappointment and anger and the shouting that I do, I'm also very concerned that people have to pass. And unlike some of you others have performed very poorly in their midterms and the quizzes. So the term paper becomes a mechanism to jack up the grades. And some of the term papers are not so good, and some of the papers, some of them are reasonable. But the marking has been exceptionally liberal. As has been forced upon me, I should be honest and say this, because of either whatever class performance being not up to my expectations. So can you see the screen?
Yes, sir.
Oh, so this is where we were, right? Let me sort of remove this. So essentially, I think I will sort of go back a little bit and say that, and this is, I mean, actually unnecessarily complicated. So yeah. So essentially what I was doing was that I was trying to say that there are two things here. One is the macroscopic constants and one is the microscopic constants. And I was trying to sort of distinguish between the two, the microscopic and the macroscopic. Now remember, the microscopic constants, microscopic binding constants are actually in a sense what is happening, binding, but really the problem is that you can only experimentally observe the macroscopic ones. So other than conceptual understanding, the microscopic binding constants by themselves yield nothing, and therefore you cannot sort of talk about their values. For example, it's not easy to measure. For example, I mean, as I said, you have an enzyme, a dimer, right, and neither of the sites are occupied. Now, ideally, it could go to this and this with say one site occupied. This one. शुरू हो गया पहले से. अरे, this is not good. And or it can go to this with this site occupied. And then, of course, both of them, I mean, I'm making the simplest of pictures, and of course, they will be also reversible. Both of them will be going to the W occupied system. The problem is that this is, say, I mean, according to the book, D00, right? And this is D10, occupied, unoccupied. This is D desired states, I mean D01, and this is D11. But as far as experimentally you are concerned, these two things are all, I mean, you cannot distinguish between whether it's bound here or whether it's bound here. You can find out the measurable states are D00 and this plus this second state and the D11. How much is half occupied, how much is full occupied, how much is not occupied. So the macroscopic parameters are the so if you look at the macroscopic parameters and the microscopic parameters that I was talking about was that this was, you know, this I mean, remember for the 2 to 3 I was talking about 3 states the last class. I should have actually continued, but let me do it separately. I will use different terminology, but the concept remains the same. Now some Ka, the association constant, is some D10 upon D00 into S, right? And Ka is also equal to D01 upon D00 into S. Do you follow this argument?
Yes, sir.
Yeah. So the real point that I'm trying to make is that I sort of wanted to call this as K1 and K2. I mean as K1 and K2, the microscopic binding parameters. But the macroscopic binding parameters Okay. Or maybe it's a dissociation, association constants would be what? Would be some K, right? And this will be this plus this. D10, this will be equal to, sorry, D10 plus DO1, right? Upon, क्या हो रहा है ये आज? Upon DO1 upon D00 into S. Or K2, D00 into S. You understand what I'm trying to say, right? So this is K1. Then this K2, these are the macroscopic parameters. K2 will be also equal to what? D11 or this thing here divided by D10 plus D01. This is one single concentration which you can't measure upon S. Are you getting this argument?
Yes, sir.
So you can see that Ka and K1 are related how? You can see that K1, something is wrong with this pen today. When I'm writing, it's not coming. Use a different colored pen. K1 is you can see 2Ka, right? You can see this, right? Very obviously. This is Ka, this is Ka. I now have not changed the values. See, I'm taking Ka in both cases to keep it simple. Last class I was keeping them different. But suppose they are equal, then the microscopic parameters Ka plus Ka, D10 plus D10 here. Right? D10 plus D10 upon DO. So you can see that K1A is equal to 2Ka. Is that obvious? Right? And so therefore, and on the other hand, the reverse is true. K2, this one here it is the other way around. It is half Ka. Okay. Can you see? Can you follow this argument? Because you know you will have this 1Ka for this, 1Ka for this, and so both of them are leading to this. So you know this here, this by this, and this by this. And so I derived that expression for you. When it goes up, it is going to be a trouble. Sorry. It goes up. When it goes up, so I remember I derived 1 upon capital K will be equal to 1 upon K1 plus 1 upon K2 plus 1 upon. What is gone wrong with this computer today? So 1 upon K2 plus 1 upon K3. I'm sorry, this is getting a lot of trouble. I'll sort of rub this out and sort of, no, I will not rub it out because then. So remember, so therefore, there were three ways in which you could achieve the second and the EA, as I was calling it now. Now I'm calling it D0. So you could have EA, where it's stuck EA here, EA here, EA here, or EA here. That is what I did in the last class. Remember?
Yes, sir.
So there were three ways. So each of these. So therefore, you got 1 upon K is equal to 1 upon K1 plus 1 upon K2 plus 1 upon Kc. So you got that K is equal to 2K. You can get K is equal to 3K. If these were Kas. So the microscopic binding, real argument that I'm trying to make is simple. That the microscopic binding parameters A are non-measurable, and therefore, for all practical purposes, you have to keep them as, you have to assume that they're equal. So the K12s and the K21s and all those things that I was deriving, you have to assume that they're all equal. And so the drawings that I made a simpler drawing this time. The last class I drew a much more complex drawing. If you want me to go back to that, I can do that. But really the issue is that the macroscopic binding parameters are combinations of these parameters. Right. And if you look at it very carefully, then really there are two steps, two ways in which you can create D1, right? Now this is a point that I want to make actually without doing the tedious algebra, which is that I have what are the number of states. For example, if it is a enzyme like this, then I can have two states for single occupancy. This is occupied, this is occupied. Suppose I have 3, then I could have this occupied, and this occupied. Right? And suppose we had 2 occupancies of these, or let me ask the more simple question. Suppose we had 4 and we want 1 occupancy is just 4 of them, right? 0 occupancy, only 1 state. 0 occupancy, only 1 state, all of them are 0. 1 occupancy, it could be occupied here, it could be occupied here, it could be occupied in the 3rd place, and it can be occupied in the 4th place. And of course, for 2 occupancies, it could be here, 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 here. So now you know the argument, right? It is NC2, right?
Yes, sir.
Or NCI is the number of occupied states possible when you have I states being occupied. So the number of ways in which you can go, and so this is the argument that I'm trying to make in a simple way before I move into this, and this is the background that you need to have. So I am going to go from and n is the number of sites, sorry, n is the number of sites that I have, and I is the number of occupied sites, and the number of ways in which you can design such a strain is NCI, right? Here it is 2C1, yes. So there are 2, right? And so what you are going to go is from a I minus, so breaks my rhythm, from an I minus 1 state, I minus 1th state to the ith state, right? For example, from 2 to 3. Say let us there are 4 of them. So how many ways can you have 4? And you can think about that. So it is NC2, and from NC2 it will go to the ith state where there are 3 sites occupied. So A and various A's and all that, and now you will have one more A added to this. So the number of sites for ith state and I minus 1th state are NCI and NCI minus 1 respectively. Right? So from here it will go to here. So in the simplest situation that I can think about, and without drawing it like a child, suppose we should draw it actually, this keeps it simple. Suppose we had 3 states. The way 3 empty states can go to, so NC 3C0 can go to 3C1 in 3 ways, obviously. You realize? Because 3C0 and 3C1. 3C0 is 1, factorial 3 by factorial 3. And 3C1 is 3. Now, this can go to 3C2 in how many ways? What is 3C2? 3 again. Are you getting this argument?
Yes, sir. Yes, sir.
So the point that I'm trying to make is that if the microscopic binding parameters are all equal, K12 equal to K21 equal to and so on and so forth, then for all practical purposes, if all the Ks are equal, then the relationship between the microscopic and the macroscopic binding parameter is simply a matter of distribution. It is essentially a statistical argument. It is essentially a statistical effect. Okay. So it is, क्योंकि आप जब डेरिवेशन करेंगे तो आपका ये अभी जो मैंने अभी डिराइव किया आपके लिए with the one which I derived just now. So I will go back to this one. Let us do the 2 1. So what did we get? So this was Ka, this was Ka, this was Ka, this was Ka, this was a Ka prime, let us say Ka prime. And you could see that whether K1 was equal to 2Ka, right? Small k tha ye, hai na? Or K2 is equal to half Ka is essentially a statistical effect. Are you getting this argument? No. Yes. That is why I was deriving.
Yes, sir. So if let us put some numbers here. So if say n is equal to 4, that is the usual hemoglobin argument. Let us say n is equal to 4, and the number of ligands, as I say, 2. Then we agreed that there will be 6 ways to arrange, and suppose I is equal to 2. I mean 2 places. So essentially, I'm saying this is the with S being in 2 places. S, and this the total set of arrangements will be 6. Right? Yes, sir.
Okay, and M3 is how many? And suppose I is equal to 3. How many?
4.
4, right?
Yes, sir.
Right? And so M3 is this is then and M3 is I is equal to I is equal to 2, then we have arrangements possible, 6 possible arrangements, and then with I is equal to 3 there are 4 possible arrangements. Now, so we know this now. Now tell me what are the values of macroscopic constants for between Mi, let us say this is stage 1, Mi, this is this one, to Mi plus 1, or rather let me write it like this. Mi is so now I will rub this out, rub the top part out. So the argument that I'm trying to make is now simple enough. I am saying that Mi is now going to is actually being achieved from, rather not going to. So it is being is being achieved by Mi minus 1 plus S, right? And so for this equation, the macroscopic binding parameter Ki is obviously Mi minus 1 S upon into S. Yeah, this is going to get too much of irritation today. Should throw this upon Mi. Are you okay with this?
Yes, sir.
And now what I'm going to ask you is that if I had this transition taking place with the microscopic KD dissociation parameters, KD, and they were all equal, tell me what is KD in terms of, let us say, Ki. What is the relationship? Can you tell me?
Sir, can you please repeat the question?
I am saying that, okay, sort of. Let me actually do it. Actually, this is obvious question, but I thought it is. I am saying that let us assume, let us assume a simple situation that I have n equal to 4. N equal to 4 and 2 sites are occupied. And then it goes to 3 sites are occupied. So I is equal to 3. And I minus 1 is equal to 2. So I am saying that the macroscopic binding parameter is this
two sides occupied, and two sides are occupied in how many ways? I mean, drawing that would be irritating, but I am sort of drawing two of them at least, and so on and so forth. And so S is here, 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 and there are 6 such possibilities. 4 into 3 upon 2?
Yes, sir. Yes.
And these are now going to all attach with A plus A here, and go to, for example, this will go to this, and this will go to this, or whatever, and so on and so forth. So all of these are the microscopic states, right? The microscopic states, these are all microscopic binding parameters, KD, and let us assume that all these KDs are equal. So how many states and how many states there? So really, I have, what was the dissociation constant? Remember how I did it? What is macroscopic parameter? What is the Ki, the macroscopic? It is Mi minus 1 into S upon Mi. But Mi minus 1 is the summation of how many combinations for this case?
6 combinations.
There are 6 combinations. There are 6 structures. I will call them 1, 2, 3, 4, 5, 6, like that. Into 6, into S, divided by Mi is a combination of 4 structures. And these, the ratio between these individual equations is actually the I, the KD. With individually, when they transition from this, remember that argument that I was making, that EA was going to plus A was going to EAA by a K12, and so on and so forth. So there are 4 such states and there are 6 such states, and all the binding constants are equal. So I'm not going to do the tedious algebra here, and simply say that I will, if they're all equal, that algebra becomes rather simple. If all these K12, K13, K1 all become equal to KD, then my life is very simple. Then it is just a statistical effect. Right? So KD is equal to, so I hope you follow this argument now. So the KD, that is the microscopic binding parameter, is equal to KD, remember this is here, is equal to Mi minus 1 divided by the combination, the NCR, right? Into S upon Mi into, sorry, this is NC, I should not call it R, I should call it I minus 1, and NCI, and that is it. Are you following this argument?
Yes, sir.
Sorry, divided by.
Yes, sir.
Sorry, divided by. Huh? ठीक है ना? And so we can see that Ki is equal to NC I minus 1 upon NCI into KD. So I without doing all that tedious algebra, by that assumption that all KDs are equal, because finally we have to put them all equal. So instead of doing it in terms of K1, K2, K12 and so on and so forth, I just sort of thought that I would simply present the statistical interpretation. The Hans Risinger book, that other book, has this derivation in a more tedious algebraic form, but I thought this is a simpler version. Is this argument clear?
Yes, sir.
Yes, sir.
So obviously you can see, for example, for 4 situations, you would have K1, the capital is 1 by 4 KD, and then K2, because all the dissociation constants are equal, is equal to how much? For 2, let us say we have 4, then 2 by 3 KD. Okay, क्या होगा बताइए, आप लोग derive करिए. This is simple enough. So is it correct? K2 is equal to 2 by 3 KD. NC 1 minus 1, I minus 1 upon NCI. And then obviously K3 by symmetry will be equal to 3 by 2 KD. Am I going too fast? And K4 by again by symmetry principles will be 4 upon 1, that is 4 KD, right?
Yes, sir.
Right? So this is derivable from this expression here. Right? And so these are the essential relationship between microscopic and macroscopic constants, with the assumption that and of course NCI minus 1 upon NCI is also can be also rather simply can also be written as Ki is equal to, I hope you know this. What is Ki? What is the simplified version? Ki is equal to Kd I upon n minus I plus 1, right? Sorry, n minus I, na? N minus I plus 1. Obviously, this is NC. What is NC? What is NCI? Is this all right? I rubbed this out. NC, क्या था ये? Hello. What is NC I minus 1 upon NCI?
Yes, sir. NCI minus 1 upon NCI into KD.
Yeah. So is this all right? Ki is equal to I upon n minus 1 plus I. Right? Factorial n upon factorial n, sorry, n minus I into factorial I, and then divided by factorial n minus upon factorial n minus I minus 1. अरे आप लोग करके बताइए, मेरा पेन नहीं चल रहा है. So can you derive this expression? Simple enough, or is it wrong? Hello. Can you derive this?
This above equation I'm not getting. Like Ki is equal to Kd into I upon n minus 1 plus I. It is not coming.
नहीं आ रहा आपका? अच्छा, चलिए, let us do this then. So what is the expression for Ki? What is this expression? First tell me what is the original expression.
Ki is equal to Nc I minus 1 upon Nci into Kd.
Upon Nci into Kd. Now what is this expression equal to? This is factorial n divided by factorial n minus I minus 1 factorial into I minus 1 factorial divided by factorial n divided by factorial n minus I factorial into I factorial. Is that all right?
Yes, sir.
Right. So इसको simplify करते हैं. ये आप लोगों ने जरूर वो JEE टाइप के एग्जाम में देखा होगा इस तरह के सवाल. So what is the simplification of this? This is equal to, this goes away. So n minus I factorial into I factorial upon n minus I plus 1, right? N minus I plus 1 factorial into I minus 1 factorial. Now what is I minus 1 factorial upon I factorial? I factorial upon I minus 1 factorial? It is nothing but I. Right? Because 1, 2, 3,
Yes,
4, 5. And what is n minus I upon n minus I plus 1 factorial? That is n minus I plus 1 factorial. 1. That is all, right? ठीक है ना? तो ये आ गया ना एक्सप्रेशन?
Yes, sir. Yes, sir.
तो ये कोई कठिन काम नहीं है, लेकिन आप लोग थोड़ा सा अलजेब्रा प्रैक्टिस कर लीजिए अपना, है ना? So you can find out the relationship between, as I said, the one that I was doing for the 3-state system that I was doing yesterday, and you can actually prove that, for example, remember the 3 states EA वाला जो कर रहा था मैं, ये 3 वाले स्टेट थे, आपको याद होगा, है ना? तो instead of deriving the more tedious expression which is there in Hans book, in the Hans book, you can very clearly and simply say that, for example, K1 is equal to Ka by into 1 by 3, right? But 1 upon 1, ठीक है ना? ठीक है ना? I is 1, n is 3, minus 1 plus 1. ठीक है ना? I is 1 plus 1. So 1 by 3, and then K2 is equal to क्या होगा? 2 is equal to Ka. ठीक है ये? If I is equal to 2, just use this expression and substitute. 2 upon 3 minus 2 plus 1. ठीक है ना? And K3 is equal to Ka into 3.
Yes, sir.
ठीक है?
Yes, sir.
So this is how we sort of find out the expressions of these things. Now let us go down to, let us quickly now move to what we will call, this is the relationship between microscopic and macroscopic constants. And now let us go down to the models. And one of the simplest models of cooperativity concept, rather actually not the model, is the Adair equation. ठीक है? क्या लिख क्यों नहीं रहा है? Adair equation, right? And the Adair equation is rather easy and simple to understand. So the basic argument is that let us go back to our basic idea of saturation constants, saturation. And so again we have this whole argument. Now we come back to macroscopic constants, and remember what we wrote? We wrote, I will write it, so it doesn't matter, E plus A, and we had the macroscopic constant Ea. These are the macroscopic constants, right? K1, Ea. Because this is of course only one way, but for example, Ea plus A is K2, Ea2. There are 2 ways to get Ea2, but we are not going to bother about that, and so on and so forth. And Ea2, as I said, sequential binding, Ea2 plus A and is equal to K3 and Ea3. Are you following this? This is what I wrote in the last class, and so on and so forth till we get Ea n minus 1 plus A is Kn. Okay, the macroscopic binding parameter Kn, which is going to give you Ean. Okay, and so all these things can now we can put the dissociation constants and we can say EA is equal to the other way around, right? E into A upon K1 and EA2 is equal to EA into A upon K2, which is equal to what? Which is equal to what? What is EA? E into A. I'm just going fast, that is all. Upon K1, K2, which is?
Yes, sir.
Which is EA square upon K1, K2. And I hope you can see now that therefore here the EAN, this EAN here, I hope you realize this, EAN here will be equal to what?
EA2 got X upon K1 to Kn.
Yeah, E raised of AN, and then we have K1, K2, K3, K4, till K, right? Is this all right?
Yes, sir. Yes, sir.
So now we can look at the saturation constants. And what is the saturation constant? The saturation constant is the I told you the bound A by ET. The bound A by ET is the total bound substrate. The total bound substrate. The total bound substrate A bound, which I was talking about in the last class. Now A bound now is equal to, remember, EA bound with this, then two molecules are bound here. So plus 2EA2. You follow this argument? Plus 3EA3. Are you getting this? So
Yes, sir.
this molecule, the EA state binds 1A. The EA2 state binds 2 A's for each molecule of E. For each molecule of the complex, there are 2 A molecules. So the A bound is equal to EA plus 2 EA2 plus 3 A3 and so on till NEAN. And the total enzyme is, of course, the free enzyme plus EA plus EA2. Now notice, here there's only one enzyme. Here there's only one enzyme. So EA2 plus EA3 plus so on and so forth. And so on and so forth. Is this okay? Right?
Yes, sir.
Right. So this is your bound enzyme and this is your bound A upon ET. That is what we are trying to calculate. Now, and then we can use these equations here and we can substitute this. So I will love this part out because I want to hold this one. So what do we get in the Adair model? So we get A by ET equal to what? We can take E out here the same way E can be taken out the way we did earlier, and E, and that first one is A by K1. These are macroscopic binding constants plus 2A square by K2 plus, are you following this? No, sorry, not K2, K1, K2 plus 3A square 3A cube.
Yes, sir. 3
by K1, K2, K3, right, and so on and so forth. Okay?
Yes, sir.
Follow this argument?
Yes.
Yes,
And
sir.
divided by, and I can take E outside again, right? What do we get? E outside 1 plus, okay, 1 plus a by k1 plus same thing a square, but no 2 here, a square upon k1 k2 plus a cube upon k1 k2 k3 and so on, sorry, k1 k2 k3 and so on and so forth, and this e's can get cancelled out. So a by et is now, so you can see this is the expression here. So a, this expression here, a by et, can be understood as this expression here, right? How do we write it? I hope you are familiar with this. You are surely familiar with a by et is equal to, this is summation I equal to 1 to n, right? And I is increasing, so it's I, right? A raised of I raised of 2a square, a raised of 1, 2a square, 3a cube, 4a 4 raised of 4. So I a raised of I, right? And then in the bottom of it, inside this summation sign, of course, this is bracket here. In the bottom of it, it is pi ki, right? J is equal to 1 to 1 to I. Okay. J is, because this is K1,
Yes.
K1, K2, K2, K3, K3, and so as I increases, I is equal to 1. So this becomes pi Ki. Okay. This is your top expression.
Yes,
and
sir.
the bottom expression is, yeah.
1 plus
And the
AI
bottom
by
expression,
pi.
1 plus summation, summation AI
Upon pi
divided
ki.
by pi Ki.
Yes, sir.
This is your basic expression. Because of course we are assuming K1, K2, K3 are all equal to KD. So that is one issue there that we have to remember. Now can you simplify this? Can you simplify this into a meaningful expression? So basically what we have got, A here is the number of bound sites. So notice that A here, A bound represents the total. So ET here represents the total sites, and this represents the bound sites. The number of sites which are bound, and this is the number of sites which are total. Is this argument clear to all of you?
Yes, sir.
So now can you sort of do it for say 2 molecules or 3 molecules? Can you do it for 2? So can you now, I mean, I'm not going to derive this for you. For example, let us take the same old problem that we took. Can I rub this out? This is a generalized expression. Yeah, this is a generalized expression. Now, can you, for example, tell me this old problem that I took just now? I mean, whatever. What is the expression? This, remember this became this and this with one S here, and this. Let us solve the easiest one, S here, and then I got SS here. Remember this problem? Okay, and the macroscopic parameters are K1 and K2. K1 and K2. So this is this sum is, so this is K1 here, this is K2 here. So now tell me what is the fractional saturation? Let me call it bound upon unbound, let me call it Y. What is that equal to? What is the expression for this? Hello, can you understand the question?
Yes, sir.
Yeah. So I mean this is a generalized expression, and I want you to sort of derive in terms of say S. Can you derive this? I mean, I'm just sort of asking you, for example, for 2, I'm going to write the expression here, and I want you to do this for me. So I'm going to write it K1 S plus 2 K1 K2. I thought this is obvious. S square upon, ये भी सीधा से लिखा हुआ है यहाँ पे, two into upon 2 into 1 plus 1 plus K1S plus K1 K2 S square. Okay, from here, this expression here for two systems, just the first two terms. Okay, this is all that will be required for the two system. This term, this term, this term, this term, this term. Right? So for two systems, this is all that is. So this is called the Adair equation. And for a dimeric protein with macroscopic association constants. Okay. And now you know that the macroscopic association constants K1 and K2, this is K2 here, remember? K1 and K2 here. For I'm just solving for 2. So, and you know that K1 is equal to, the macroscopic K1 is equal to 2K1, small K1, and K2 is equal to, and K2 is equal to half. Just now we derived this half K1, right, for microscopic. So can you write this in terms of microscopic equations, binding parameters, and assume that they're all equal?
Yes, sir.
हाँ लिखिए, इसको मैं मिटाऊं, and then I will leave you with the more minor but very obvious task. I'm going to do it. I'm going to do the simple job now. I'm going to leave you with the. So this is what y is equal to. Y is equal to K1. So बताइए 2 K1. Please tell me 2 K1S plus 2 K1 K2 क्या होगा?
2 K1 square.
K1 upon 1 upon 2 K1 है ना?
Yes sir.
कैंसिल हो जाएगा ना? है ना?
2 K1 square.
S square ठीक है?
Yes sir.
Upon ये 2 मैंने मिस कर दिया है ना? 1 प्लस, क्योंकि ये 2 क्यों लिखा मैंने, मुझे समझ में आ रहा है आपको? नहीं, मैं 2 कहां मिस कर दिया? Remember I said bound sites, but the amount each enzyme carries how many sites? 2 sites. So earlier I was doing E total, but E total, if this E is E total, E total is, if E total is the total amount of enzyme, the total amount of total sites is equal to 2 into E total, right? Because each of them has 2 sites. So I put a 2 here. Are you getting this? Hello?
Sir, so every time we will multiply.
We will now suppose there are 4 sites, then we will have to multiply. So because we are finding out bound sites, A bound, which is number of bound sites, divided by total sites, not total enzyme.
Okay sir.
Total
okay.
sites, which is not, so which is equal to N into ET, where ET is the total amount of enzyme.
Okay sir. Okay.
Right, you get the argument. So
Yes,
I mean, if this molecules of enzyme agar ET hai, so into N, where N is the total number of sites available. So 2 plus
okay sir.
1 plus 2 2 K1S, right? Plus again the same thing, plus 2 plus this expression here. K1 square, I will simply write it as K1 square S square. ठीक है ना?
Yes, sir.
इसको सिंप्लीफाई करिए, ये तो घटिए कम से कम, क्या होगा ये? क्या है बताइए? K1S
Plus
1 plus K1S अपॉन ये है 1 प्लस, अरे ऑब्वियस है 1 plus K1S होल स्क्वायर. Does it make sense?
Yes, sir.
Which is equal to K1S upon 1 plus K1S.
Yes, sir.
तो ये वही आ गया ना, हाइपरबोलिक रिस्पॉन्स आ गया ना, वही Vmax वाला आ गया ना आपके पास वापस.
Yes,
अगर
sir.
हम सब माइक्रोस्कोपिक कांस्टेंट सेम लेंगे तो ये वही V1S वाला आ जाएगा. एज ए मैटर ऑफ फैक्ट, नाउ आई वांट यू टू थिंक अबाउट दिस एक्सप्रेशन हियर. Now this into n, remember, into n, ठीक है ना, बिकॉज ये ए बाउंड, तो e बाय बाउंड साइड et किया था, अब अगर टोटल साइड्स करेंगे तो ये n से मल्टीप्लाई कर देंगे. इज इट ओके विद ऑल ऑफ यू? आर यू फॉलोइंग दिस?
Yes, sir.
And remember ki and ki here, ki, remember ki multiplication, and remember that ki in terms of k1 क्या होगा? That's the question that I'm going to ask you now. Now I want you to think a little bit in terms of your binomial. You remember your binomial? हेलो, बाइनोमियल याद है आप लोगों को? नहीं याद आ रहा है. चलिए मैं याद दिलाता हूं, because I have to finish now. And I'll leave you with this very minor and some very obvious exercise. Now you remember this expression here? This expression, can you see this? This is the bottom one here. This one you can see. So this pi k, अरे भाई क्या हो रहा है? Pi ki है यहाँ पे, a raised to i pi ki, right? Pi ki दोनों जगह है. Now think about pi ki in terms of k1. What is ki? In terms of ki minus 1, अभी हम लोगों ने डिराइव किया था, भूल गए आप लोग. See, I have to, ki is nothing but, for the pi ki is nothing but k1, k2, k3. For example, let me write only 4 of them. And what is k1 equal to in terms of, what is k4 equal to in terms of k3, k3 equal to in terms of k2, k2 equal to in terms of k1. Do you remember that? What did I write? I'm waiting for you people to respond. What are these in terms of microscopic parameters? Hello. n minus I plus, अरे भाई साहब आप लोग अगर बताएंगे नहीं तो बड़ा मुश्किल होगा. n minus I plus 1 upon I of course a raised to I upon kd summation pi. अगर मैं ऐसे लिखूं तो ठीक है ये?
Yes, sir.
लिखा था. Yes, sir. Are you getting this argument? So,
Yes, sir.
So every time you have to simply keep on multiplying. See, this this into this into this. Each of these is a multiple in terms of this fraction here. So I want you to go back, and I'm not going to derive it in 2 minutes flat, 1 minute flat, and think about K4, its relationship with K3 as Ki and its relationship with Ki minus 1. Right, what is the relationship? And therefore, if I want to multiply Ki into Ki minus 1 into Ki minus 2 and so on and so forth till K1, then what is the expression that I will get in terms of Kd? Finally, we'll get it in terms of Kd, right? Okay.
Yes, sir.
Okay, so I want you to go back and derive this complicated expression here, How does it simplify in terms of if Ki and Ki are written in terms of Kd? And come back and tell me. Next class we will wrap this up.
Sir, can we have some questions on this? Like,
नेक्स्ट क्लास में अभी ट्यूशन कब होगा भाई? वक्त तो है नहीं.
नहीं
इस पे
sir.
आप लोग हाँ.
Just for us to solve, you don't have to sir like solve it.
Okay. Whenever you tell me, let us meet in the next class on Friday, and then we will decide. That is the last class. After that, Saturday or whatever day you feel is okay, we will meet. Okay.
Okay, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.